Hello and welcome to my presentation on OpenCL. This presentation will introduce the concepts and features of OpenCL and give some background on the platform's development. Some code examples will be presented that we're creating using OpenCL's C-based language. These examples are used in the matrix multiplication algorithm, which is used to calculate the speedup associated with utilizing OpenCL instead of sequential computing. OpenCL will then be critiqued and potential shortcomings discussed, then similar products will be presented as potential alternatives. OpenCL provides support and functionality for systems that contain multiple processors, such as a combination of GPUs and CPUs. It views these as heterogeneous systems and can also function if the CPU and GPU are from different providers. Matrix multiplication is a common benchmark to measure system performance, as the dimensions of the matrix can be easily changed, increasing the complexity of the task exponentially if the matrix is a square. As computers have evolved and been utilized for more complex tasks, there has been a rise in demand to be able to perform these tasks more efficiently. For instance, a lot of scientific research requires data modules and simulations that require a large amount of computing power to complete within a reasonable time frame. Computer systems usually contain a combination of central processing units and graphics processing units. These units can be produced by different providers. They are referred to as heterogeneous systems as they contain more than one type of processing unit. More efficient programs are usually achieved by a combination of parallelization and intelligent memory operations. Different systems also provide different methods of memory management, which use different hierarchies for interactions. Managing complex tasks often requires memory operations, such as read and write, which need to be managed by the parallel processors in a way that prevents any memory leakage and is also efficient as possible to reduce any latencies. There is a need for a system that is capable of managing the parallelization of these complex tasks, while also ensuring any memory operations are secure and efficient. OpenCL was developed to meet this need. OpenCL was initially released in April 2009 by Apple, and it was included in the OS X Snow Leopard operating system. After it was released, platforms such as NVIDIA, AMD, and IBM, and others, announced support for it on their products. The second most recent release was OpenCL 2.2 in May 2017. However, the release was not popular, and between now and then, none of the companies that supported previous versions of OpenCL integrated support for version 2.2 into their products. The most recent release of OpenCL was a new step for the platform in that it reverted to the core of the 1.2 release, making all the features released after that point optional and it completely backwards compatible. Another reason for this recent rollback is the difference in user base since its creation. Apple has since stopped using OpenCL and now uses its own proprietary Metal API for their operating systems. The platform is now developed and released by Kronos Group, which is a combination of many different companies that produce and use OpenCL. Most of the main processor manufacturers, for example NVIDIA, Intel, and AMD, support OpenCL and provide free downloads for the drivers required. The Intel drivers are open source and as such are more up to date than others. OpenCL is still widely used by companies such as MATLAB, Texas Instruments, Sony, Adobe, Samsung, Wolfram Maths, and is still relevant. OpenCL can be used for a diverse range of applications, including as a baseline to create higher-level object-oriented language such as C++. It also provides a C-based language and API to allow developers with experience in C to be able to adjust to using OpenCL more easily. The main purpose of OpenCL is to provide a standard API and set of guidelines that can be used for different applications over different processor types from different manufacturers. The following section of this presentation will show examples of OpenCL code and demonstrate how the different components of a system implementation work. The code examples used are pulled from the matrix multiplication script used to test the speed of the OpenCL implementation when compared to a sequential implementation. OpenCL systems consist of 5 main components. These are the compute device, the program, the kernel, the context, and the command queue. A compute device is what tasks are run on. It consists of a CPU or GPU, can be either, and receives instructions from the host processor. It can contain multiple compute units that in turn contain multiple processing elements. These components of the compute device are used for the parallel processing of the allocated task, allowing the task to be logically split and executed across processing units. The code snippet shows how available devices are extracted from the host machine. For example, when run on my personal laptop, it returned one compute device, which is my integrated Intel GPU. The context component can be conceptualized as representing the environment in which the compute device exists in. It contains the compute device, kernels, command queues and programs, and assists in communications between the components. It can also be associated with one platform at a time, meaning it is specific to the device it was created with, as shown in the code snippet. The program contains the instructions for the required task. This can contain multiple functions and require inputs. The example shown defines the matrix multiplication operation and requires 3 inputs. The program creation uses the string as the source code input. However, this could also be achieved by reading from a text file. The program is created from the source code before being built with an extracted device. The kernel refers to the function run on a compute device and is capable of running multiple processing elements contained on the device concurrently. Kernels are created from programs before being allocated to the device and have the ability to manage device memory. The kernel creation involves calling the program object created previously and using the second argument to specify what function will be run on this kernel. As the example program only had one function, it will be allocated to this kernel as specified in the command. The matrix mult function has 3 matrix arguments denoted A, B, and C. The second line of code shows a buffer being created for the first matrix, which reserves a space of n by n double elements and denotes it read-only. This buffer is then used to set memory for the first kernel argument, which is the first matrix. This process is repeated for the second matrix input and the third matrix input. The command queue is how the host processor communicates with the compute devices. A queue is created using the relevant context and device variables, and kernels and other actions are added. The buffer write operation is then added to the command queue to ensure there is memory available for the kernel operations. The enqueue functions also take an event variable as an input, which can be used to track when the task is completed, and to check if there are any errors in allocation. The last line of code shows the operation of extracting the resultant matrix from the device back to the host buffer using a queued read operation. This is the main way of passing information between compute devices and host operation, and there is a slight latency associated with this. OpenCL uses 4 main types of memory: global, read-only or constant, local, and private. Global memory is accessible and shared by all processing elements and devices in the system. The read-only memory can only be written to by the host processor, but can be seen by the rest of the system. The local memory is shared by a group of processing elements completing a task. For example, the processing elements completing the matrix multiplication task. Private memory is specific to the kernel and can only be accessed by its specific kernel. A matrix multiplication was performed using 2 matrices of 1024 by 1024 elements with 4 by 4 work items in the work group. This operation was also performed using a best possible sequential algorithm to calculate the speed up. This was run 10 times, and the average time was taken from these operations to use for calculations. The OpenCL runtimes included the time taken to copy the relevant memory from the host to the device and back again. The speedup was calculated to be 55.84, and the time taken to execute using OpenCL was 0.45 seconds compared to 25.23 seconds. To contrast this, a smaller example using 4x4 matrices with the same 4x4 work items in the work group, the speedup is a very small number, so OpenCL is not recommended for these contexts due to the high overhead of memory operations required to use OpenCL. Some critiques of the language is that the nature of the language means that the code is very verbose and low level due to the setup and cleanup required for all the individual components. As seen in the matrix multiplication example, the overhead introduced by the memory operations can make using OpenCL for smaller applications not practical when compared to normal sequential operation. Another factor is the time between releases. Given the last release before this year was 3 years ago, OpenCL is not often updated. Similar products to OpenCL include CUDA, which is an architecture built by NVIDIA for NVIDIA products that functions in a similar way using kernel-based execution. It is currently more popular than OpenCL when it comes to NVIDIA devices. However, it doesn't provide functionality for other platforms like OpenCL does. OpenCV and OpenGL are based on the OpenCL language and are used for computer vision and graphics processing respectively. In conclusion, OpenCL was created as and remains to be a powerful tool for parallelization. It produced an impressive speedup of over 55 when used with a matrix multiplication example. It was found that while OpenCL is very helpful for large datasets, the latencies are impractical for smaller tasks. Despite its verbose and complex code, OpenCL is still a valuable platform when compared with the alternatives on the market. Thank you.